Good morning. Today we're going to start circular motion. This will be the biggest change in terms of what we've been studying since the beginning of September. So your goal today is just to make sure you understand the basic terms and how to do some simple calculations with them. I want to start out by making sure you understand that there are two different contexts that we can use for the word speed. So when I say these two cars have the same speed, it could mean one of two different things, so make sure you know them both. First one is the traditional sense of the word speed. These two cars have the same speed. If we were in the cars looking at the speedometer, they would both read the exact same number. However, it looks like the red car is going faster, but that's a product of the fact that it's in a smaller circle. The blue car is traveling just as many meters each second. It just is traveling in a bigger circle that has more meters in it. So they have the same speed. This is called linear speed. This is measured in meters per second. The second way we could talk about speed is to say these two cars have the same speed. Not the speed that you would see on the speedometer. If you were in those two cars, the blue car would have a higher speed reading on the speedometer. But you can see they are keeping up with each other as they go around the circular paths. This is called angular speed. Both of these cars have the same angular speed. They're both covering the same amount of circle, not in terms of distance, but in terms of angle per second. Okay? So this is the same angular speed, and the previous one was the same linear speed. Linear speed is in meters per second. Angular speed could be in things like degrees per second. Okay? Let's delve a little deeper into angular speed and how to calculate it, and also how to calculate linear speed for objects moving in a circle. So we want to start with a new term. It's called angular displacement. It is very similar to displacement that we had before, when we had delta x or delta y, but now it's simply the change in angle instead of a change in position. If you look at the car, it starts at 0, and as the car travels, it's going to bigger and bigger angle positions in this circle. Your change in angle, your angular displacement, you could say 90 degrees, 180 degrees. The car is now approaching the 270. This is very important. When the car gets back to 0, you'd call it 360. This would be 370, and so on. Do not go back to 10. Keep adding your angles as the car goes. So when the car gets back here for a second time, you're not going to call it 360, you're going to call it 720. Angular displacement. Okay, I want you to realize that degrees are very convenient. You're able to visualize them, you're able to use them, but degrees are not the standard unit for angle. The standard unit is a thing called a radian. Let me describe and show you what a radian actually is. So as the car travels from 0 to this spot, that represents an angle of 1 radian. What makes it 1 radian is this. 1 radian means that you travel a distance of 1 radius when you cover that angle. So one more time, what's special about a radian is it's the angle that causes you to cover a distance that is equivalent to the radius of your circle. All right, very, very special angle. And this unit is what we are going to use for all of our angles when we're dealing scientifically with angles and angular speed. 1 radian is the same as 57.3 degrees. Sometimes I find it easier to remember that pi radians is equal to 180 degrees, or 2 pi radians equals 360 degrees. Either way, if you have to do a conversion, like if you were converting 90 degrees in the radians, You would pick whatever one you know. You put degrees on the bottom and you put radians up top. So if I use this one, I would say 57.3 is equal to 1. Alternatively, I could have put 180 on the bottom and put 3.14 up top. Make sure you can convert from degrees to radians and vice versa. A radian is approximately 1/6 of the way around the circle, as you can see there. Sometimes we focus on one trip around the circle. So as you watch this car go around one trip, I hope you know that one trip is equal to 360 degrees. It's equal to 2 pi radians. These are both angles. If we want to talk distance, one trip we call a circumference, and we calculate that by doing 2 pi times the radius of the circle. So these are angles, these are distances. Sometimes you'll want one, and sometimes you'll want the other. Okay, part of a trip, this is probably more important because most times you don't go a full trip. So let's take our car, let's send it on a little trip around the circle. We call that distance S. We call the radius of the circle R. We have our angular displacement in there for this wedge-shaped object. And hopefully you remember from math class this formula for arc length. Realize arc length is just distance traveled by the object, whether it's a planet around the sun, a moon around the planet, or a car around the circle. This has to be measured in radians, and this should be measured in meters. Okay? So distance equals angular displacement times the radius of the circle. If you want to find angular speed that we were talking about before, what you do is you measure the angular displacement and you divide by the time. This would be radians per second. This symbol is called omega, and again, it's the change in angle divided by time. It's the same structure as our formula from before. This is for linear, this is for angular. Okay, so the two different formulas. Angular velocity, linear velocity. Okay, technically I called it angular speed. As you guys know, if I want to call it angular velocity, I need a direction. This car happens to be traveling counterclockwise. That is the direction that scientists assign positive to. So just like right was positive and up was positive, counterclockwise is positive for some unknown reason. If it's going clockwise, that one is assigned a negative. So if you want angular velocity, you get angular speed plus direction. For direction, you could use a plus for counterclockwise, or you could use a minus for clockwise. If you have to find the linear speed of something going in a circle, use the arc length formula to find out how much distance it traveled, and then divide by your time. Okay, some other terms you need to know. The term period, that refers to the time it takes for this object to go one full trip. Exactly one trip. So it is a time. It goes by capital T because it's not an arbitrary time, but it's a special time. It's measured in seconds, and again, it's the time for one complete cycle. We also have a term called frequency, and frequency tells you the number of trips per second. Normally, you'd write it as number of revs per second. That's the standard unit. However, sometimes you'll see, especially in our country, instead of doing revolutions per second, they'll do revolutions per minute. RPM, revolutions per minute. Convert it from minutes to seconds, and you have your standard unit for frequency. Okay, I'd like you to try seeing if you can get all of these different variables that we just talked about. So here is an object on a string, and just like Wally Gator, it's going to go around and around in a circle. And as it goes around the circle, you count how many times it goes around, and it turns out that it goes around 10 times. It takes 10.68 seconds to do that. So how do you get your angular displacement? 10 trips. Each trip is worth 2 pi. Okay, so 10 trips, each one is worth 2 pi. The time, 10.68 seconds. You just read it off of your stopwatch. Angular speed, you do displacement divided by time. So we just divide these two and get your radians per second. Again, don't leave it as 2 pi, but multiply out 3.14 anytime you see the pi symbol. Period is the time for one trip. So it took 10.68 seconds to do 10 trips. So you just divide, and that will get you the period. 1.068 seconds. Frequency, you do the opposite. 10 trips in 10.68 seconds. It is the reciprocal of period. So you divide these two, and whatever you get, that is your revolutions per second. To convert it to revolutions per minute, you just convert seconds on top, minutes on the bottom, and you would get RPM. Circumference of the circle, you do 2 pi times the radius. The radius is 3.8 meters. Finally, to get your speed, you do the distance, which would be 10 times the circumference. You went around 10 times. So whatever the circumference is, multiply it by 10 and divide by your time. I know I went through this quick, but it's kind of basic stuff, and if you have questions, you can ask. I'd like you to, as the final thing in your notes, to calculate all of these values for this trip. So watch it. Starts here. Ends there. So it did not even go a full circle. All right? How much is the change in angle? How much time went by? What was the angular speed? How long would it have taken to go around the full time? How many times would it have gone around per second? How many RPMs? How many trips per minute? What's the circumference of the circle? You can see the radius right here. And what is the speed in terms of meters per second? So finish that up for the end of your notes. If you have questions, just come back onto the Google Meet and ask me about them.